Before we prove the irrational numbers, we need to know the following theorem, whose proof is based on the fundamental theorem of arithmetic. Theorem 1.3. Let p be a prime number. If p divides a square, then p divides a, where a is a positive integer. Proof: let the prime factorization of a is as follows. A equals p1 into p2, and so on, pn, where p1, p2, and so on, pn are primes. Squaring the above equation on both sides, we have a square equals p1 into p2, and so on, pn, into p1 into p2, and so on, pn, equals p1 square, p2 square, and so on, pn square. Now, we are given that p divides a square. Therefore, from the fundamental theorem of arithmetic, it follows that p is one of the prime factors of a square. However, using the uniqueness part of the fundamental theorem of arithmetic, we realize that the only prime factors of a square are p1, p2 and so on, pn. So p is one of p1, p2 and so on pn. Now, since a equals p1 into p2 and so on, pn, we can say that p divides a. With this particular proof, we can prove a given number as an irrational number. Theorem 1.4. Prove that root 2 is irrational. Proof: let us suppose that root 2 is a rational number. Then, root 2 can be expressed as p is divided by q, where p, q are integers having no common factors except 1. Now, root 2 equals p is divided by q, where p and q are co-primes. Squaring on both sides, we get 2 equals p square, is divided by q square. This implies that 2q square equals p square, make it as equation 1. Therefore, 2 divides p square. By theorem 1.3, we can say that 2 also divides p. So we can write p equals 2r for some integer r. Substituting p value in equation 1, we have 2q square equals 4r square. This implies that q square equals 2r square. This means that 2 divides q square, and also 2 divides q. Therefore, we get 2 as a common factor for p and q. This is contrary to our assumption that, where p, q are integers having no common factors except 1. This contradiction has arisen because of our incorrect assumption that root 2 is rational. Therefore, root 2 is an irrational number. Prove that root 5 is irrational. Proof: let us suppose that root 5 is a rational number. Then, root 5 can be expressed as p is divided by q, where p, q are integers having no common factors except 1. Now, root 5 equals p is divided by q, where p and q are co-primes. Squaring on both sides we get 5 equals p square is divided by q square. This implies that 5q square equals p square, make it as equation 1. Therefore, 5 divides p square. We can say that 5 also divides p. So, we can write p equals 5r for some integer r. Substituting p value in equation 1, we have 5q square equals 25r square. This implies that q square equals 5r square. This means that 5 divides q square, and also 5 divides q. Therefore we get 5 as a common factor for p and q. This is contrary to our assumption that where p, q are integers having no common factors except 1. This contradiction has arisen because of our incorrect assumption that root 5 is rational. Therefore root 5 is an irrational number.